Good evening, everyone. So we'll continue with the recording of the recitation lab for week 12. So this is the outline of the presentation. We'll start by solving the exercise at the end of week 11's presentation, and we'll talk about rational functions of sine and cosine and improper integrals, mainly sections 8.7 and 8.8. So we'll cover overall 3 examples. So we'll start first of all by the exercise at the end of week 11. And here we were asked to integrate x squared plus x plus 2 divided by x squared plus 2x plus 2. We'll start as usual by uploading the file corresponding to this week's presentation as the file for week 12. Be careful, it's file for week 12, not for week 11. That's a mistake. So at the end of week 11, the presentation, first of all, for the exercise, first of all, what should we do? As usual, we should define the variables using the samples function. And here it is, we imported here from SymPy everything using the star, x as a symbol, which is a real variable. And we'll define here p as x squared plus x plus 2 and q as x squared plus 2x plus 3. And we'll try to write down what is p divided by q, okay? And then we will use this function, which is division here, div. That's a new command we have to learn. And basically, once p and q are well defined, here the div, what should it do when I give p and q as the numerator and the denominator? It will give me back what we call s and r. What is s? S is the constant you get out of the fraction, and r is the remainder divided by the denominator. So basically, this is what we get here, which means that s is 1 and r is minus x minus 1. And you could observe already that the q remained as it is, x squared plus 2x plus 2. Okay, so we have to learn this new command. So that's what we are writing here. It's then easy to see that s plus r yields plus r over q yields an integrable fraction. And notice here that s is the result of a long division and r is the remainder. And we can see also that in this example, r over q is of the form half of du over u, once u is correctly defined. And of course, here we'll define u as x squared plus 2x plus 3, which means its derivative, du, is going to be 2x plus 2. Okay, so let's define I here as the integral of s plus r over q, integral with respect to x. We'll display the integral, first of all, capital R, here it is, and then we'll do it. So this is the result of the integration. And of course, we'll talk about an indefinite integral, we should get something like this. So the result of the integration is x minus ln of x squared plus 2x plus 3 divided by 2. Okay, so from the Jupyter notebook, we had exactly the same thing. Here you see integral of x squared plus x plus 2 divided by x squared plus 2x plus 3. We defined p and q properly using our variable x. We displayed p over q. And we use the division here, div command, to display s and r. S is the result of the long division, r is the remainder, all divided by q. So this is s plus r over q. So notice that s is that little constant that is left here in our display. Of course, defining our I correctly, here I'll correct something live with you. Okay, that's a question sent by one of the instructors. So I'll run this again. And this is the display. This is the result of the division. And here I see I'm integrating s plus r over q. I'll display I. That's the integration, s plus r over q. I'll display I, and now I'll ask to do. Here we go. Okay. So I hope it's clear for this little exercise at the end of week 11. Now we'll start the material for week 12, and we talk about the integration of, we said, trigonometric functions. And here we have I as the integral of sine inverse x. And what shall we do here? We'll do an integration by parts, and we will use u du as 1 and v as arcsine. And notice that the arcsine function in SymPy is a sine. Okay. So we'll define I, first of all, as the integral of a sine with respect to x. Once x is correctly defined, v as a sine x, du as 1, and of course dv is going to be the derivative of a sine. We know it is going to be 1 over root of 1 minus x squared. And u is going to be, of course, the entire derivative or the integral of 1, which is x, of course. And once it's correctly defined, we will use the result here as res as LV, which is UV, UV, yes, minus the integral of UD. Okay, so that's what we get out of the integration. X, a sine of x minus the integral of x divided by square root of 1 minus x squared dx. And of course, now we could use the substitution 1 minus x squared. Why can we do this? Because differential u then would be minus 2x dx, and you see above here in the denominator we have already x dx. So it's going to be minus half of u. So once we perform this substitution after the integration by part, we get a simpler integral. So we first define here that r as the integral of x divided by square root of 1 minus x squared with respect to x. And here we'll perform a transformation or a substitution. We'll replace 1 minus x squared by the new variable u, which is a real variable. And we obtain a new integral we call k. So r is transformed to k. We'll display k, and here it is. It's minus square root of u. So after integration, we get minus square root of u. And once we are asked to do it, I do it, we get, of course, x a sine x plus root of 1 minus x squared. Okay, so that's what we get for example 1. Here we will repeat the same steps explained in the slides here in our Jupyter notebook. First of all, we define the integral of sine inverse. We defined v as sine inverse, du as 1, so u is x, dv is 1 over root of 1 minus x squared. This is the first result after the by-part integration, what we see in cell 16. Then we performed the substitution. We substituted 1 minus x squared by u. So we got in this part here, the second part which appeared after the by-parts integration, we will have just to integrate minus half of u, minus half of square root of u, and of course the entire derivative of this is minus square root of u. Okay, so if we adapt these things, x arc sine of x minus what we got is going to be plus square root of u, so it's plus square root of 1 minus x. And here you go. So, okay, so the next thing is the example 2 in this presentation. And here we would like to find whether we're talking about improper integrals. Here we would like to see whether or not this improper integral is convergent or divergent, and find the value if it's convergent. So what do we have? We have the integral from 2 to infinity of dx divided by x ln x. Here one can see that if we substitute u by ln x, we see something that is more clear. What happens if we substitute u by ln x? We have 1 over u. Why do we have 1 over u now in the substitution? Because the derivative of ln x is already 1 over x. So differential u is 1 over x differential x. So we get just du over u and the u integral, okay? And what was before 2 becomes limit 2 in the lower limit of the integration, okay? So now we have this integral from ln of 2 to infinity of 1 over u du. Here is our integral. First of all, I define it as the integral from 2 to infinity. That's the symbol for infinity, float infinity of 1 over x ln x. Then we'll display I, and we use this new variable, and we substitute ln x using the transform command in I to substitute ln x by u. So we get a new integral, we call it t. And now when asked to do t that do it, what should we get? We should get infinity. Why? Because the entire derivative of 1 over u just ln of absolute value of u, and of course this goes to infinity when the variable goes to infinity. So basically this improper integral diverges, of course. Example 3, we have here, let's have a look, first of all, at the Jupyter notebook. So on the Jupyter notebook, we performed exactly what you've seen in the slides, integral from 2 to infinity of dx over x and x. Here is our I integral, the limits of integration from 2 to float of infinity. We'll disconnect to produce an integral as usual. We display I. We define the new variable, u. We're going to use it for the substitution of ln x by using the transform function or transform command. I that transform calls this command. So what was previously integral from 2 to infinity of 1 over x ln x dx becomes integral from ln of 2 to infinity of 1 over du. So t that do it, we got infinity. So the example 3 now, integral from 0 to infinity of tan inverse of x over x squared plus 1. You can see that we can substitute the arctan here by u. And if we substitute the arctan by u, what do we have? We have du is going to be 1 over x squared plus 1, all times dx, which we already have. Okay? So first of all, we define the integral of arctan, a tan, using the simplify package, divided by x squared plus x, again from 0 to infinity. We display this is our integral. Now we perform the substitution of a tan by u. Once u is correctly defined, this should work. And after the substitution, that's what we get. We get the integral from 0 to pi over 2 of arctan of tan of u. Arctan of tan of u, of course, this is just the inverse function applied to the function itself. So it's u du, basically. So that's exactly what we are integrating in t here. T is just the integral of u from 0 to pi over 2. Okay. Here from the library, you could try different ways. It seems that the library is not able to recognize that a tan, a tan, applied to tan gives the identity itself. It gives u. So once we force it to do it, t that do it, we get pi squared over a. And that's exactly what's going on in the Jupyter notebook. If the integral I is correctly defined, once it's correctly defined, we perform the substitution of arctan by u. We get this. So the integral from 0 to pi over 2 a tan of u. And then we just integrate u, recognizing that we have an identity here, integral of u du. From 0 to pi over 2, which should we get? You should get pi squared of a. Okay. Hope it's clear. That's the end of the presentation of week 12. So thank you very much for following, and we'll continue with the next record. See you.